Thanks, everybody. Got to turn this on. There we go. So I'm going to talk to you today about Cat. Cat is a software developer working on a large Ruby on Rails application at BugHub. And Cat's had a bit of a stressful week. BugHub is an online community of bugs. And Cat has spent the past week shipping a highly successful new product within BugHub. But along the way, Cat has had to deal with a whole bunch of problems: data consistency bugs, slowness, at one point even site-wide failure. And all these problems stem back to this one database transaction. It'll start out as a simple little transaction, but as the days go by, Cat's going to have more business requirements that lead him to add more code to this transaction until it gradually turns into a liability for his application. Along the way, we're going to explore some of the things that went wrong and what Cat might have done differently to prevent some of these problems. The story starts on Monday. Cat showed up to work, very hungry for business opportunities. Cat knows that a lot of the bugs using BugHub are very hungry for food, but they're too busy interacting on the site to be bothered to go out to the grocery store. They want groceries delivered directly to their homes. So Cat has decided to launch a brand new grocery delivery service integrated directly into this larger BugHub product. We're not going to dig too much today into the controllers or views or how the order gets put together. We're only concerned here with how the order gets saved. So we can assume that the order instance variable here is an instance of an active record model, an order model, backed by an orders table in the database. There's also a product model, and the product is going to be identified by a SKU, a stock keeping unit. And then finally, there's a join table connecting products to orders, and that additionally has a quantity for how many of that particular item was ordered. Although it's not explicit in the code here, this call to save opens a database transaction. So if we look at the queries involved, first we see a begin statement starting the database transaction. Then it'll insert the orders and some number of order items. And finally, there's a commit if the transaction is successful or a rollback statement if it's not. And this is what a transaction is supposed to look like. It's got a few queries in it and nothing else. The idea here is we want these inserts to be atomic. We want all or nothing. We want them all to succeed or none of them to succeed. We don't want partial success. So this is all good. Cat ships this code, and all is well. The orders start rolling into BugHub. On Tuesday, Cat discovers that bugs are able to order more items than what BugHub has in stock. And this is a pretty frustrating experience. Bugs get excited about their orders, and then later they get canceled. Cat decides to deal with this problem by keeping track of the inventory on the products table, adding this inventory column. And then he can use that information to not show out-of-stock products on the site and maybe add a model validation around that as well. And then over in this submit code, Cat adds this call to update the product inventory after saving the order. And the way that works is it'll go through each item in the order and perform an update, decrementing the inventory by however many of that item was ordered for the item with that particular SKU. Cat also wants these two operations to be atomic. Either they should both succeed or neither one should. So he wraps the whole thing in a now explicit transaction. And so now the transaction looks something like this. There's some inserts, there's some updates, they're all happening together. Seems fine. Unfortunately, after shipping this code, Cat starts to see increased 500 responses for placing orders. He looks at his bug tracking software and sees things like deadlock errors, lock timeout errors, and also some requests that are taking a long time and timing out. The underlying problem here has something to do with lock contention. So this happens when multiple processes are trying to work with the same data at the same time, and so they have to compete or contend for access to that data. So we can imagine two bugs ordering the same or similar products at the same time. Their transactions begin. They create the orders. They create the order items. And then we get to this code that's updating the product inventory. And both transactions want to update the same product at the same time. The metaphor I'm using now is that database rows are like bathrooms. It usually only makes sense for one person to use one at a time. So like you enter the bathroom and you lock the door, and then anyone else who wants to use it has to wait. So that's what's going on here. One of these updates arrives first. It locks the row, which means that the other one is going to have to wait to do that update. Even after the update succeeds, that other transaction is still left waiting and waiting until finally the row gets unlocked when that first transaction commits or rolls back. So at best, contention like this is going to make the performance of transactions worse, because you can see that bug 2's transaction here is stuck waiting. It's slower than it needs to be. But at worst, it can lead to errors like deadlock errors. We have two or more transactions waiting for opposite locks, and they can't proceed. Or lock timeouts, where a transaction is waiting so long for a lock that it gives up, it times out. So lock contention here is undesirable. Interestingly, the speed of a transaction affects how much opportunity there is for contention like this. So if the transaction is very fast, the locks aren't going to be held for too long. There's not a lot of opportunity for contention. Another transaction is fairly unlikely to come in and need those same rows at the same time, but even if it does, it won't have to wait that long. Slow transactions, on the other hand, create a lot of opportunity for contention like this. There's now a lot of time for another transaction to come in and need to operate on these same rows, and that transaction might have to wait a while to get those locks. And this is what was happening in Cat's case. Cat had a lot of slow transactions. But what was making them slow? Well, one thing is that these update statements, turns out, were very slow in Cat's application. Slow queries in a transaction means slow transaction. In this case, Cat forgot an index on the SKU column. So it's kind of interesting to me. Like, you can reduce lock contention by adding an index to speed up a query. That's not obvious to me. But even if all the queries were fast, these very hungry bugs at BugHub were submitting orders with massive numbers of products in them. So too many queries can also make a transaction slow. Transactions like this are also going to hold a lot of locks. So again, the possibility for lock contention goes way up here. Furthermore, transactions like this, in addition to holding a lot of locks, are fairly likely to get stuck waiting on locks as well. And so lock contention has a way of kind of spreading. There's locks held by one transaction are going to slow down other transactions, and then that slowness creates more opportunity for contention, slowing down yet more transactions. So it's kind of a bad cycle. Operating on large batches of records like this is not something a transaction is good for. You might be able to get away with hundreds of updates in a single transaction, but if you get into the thousands, maybe you need to reconsider the design. In this case, maybe Cat could validate a max number of products it's possible to have in a single order. So it turns out this innocent-looking line can actually create some problems if it causes slowness in the transaction. Cat can reduce the possibility for this contention by speeding up the queries, limiting the number of queries. Deadlock errors are also fixable. In this case, Cat could update the products in a consistent order, and the deadlocks would go away. But Cat might also want to question his assumptions about whether this needs to be in a database transaction at all. Maybe there's another design here that doesn't require these updates to happen in a transaction, and that maybe doesn't require updating the products table at all. Like, maybe Cat needs a more robust inventory management system that lives outside of this database. Wednesday. On Wednesday, Kat noticed customers complaining that submitting an order took way too long. Nobody likes clicking on a button and waiting for a spinner. Kat tracked this slowness back to this one after create call that was doing a bunch of slow work, like syncing with an external billing platform, sending off confirmation emails, and so on. These are things we often don't want inside of a web request because they can slow down the request. We also don't want them inside of a transaction because they can slow down the transaction, leading to contention like we saw on Tuesday. So Kat moves the slow work into a background job. This is good. This is an improvement. But there's still some potential problems here. After shipping this change, eventually Kat started getting these reports of confirmation emails being delayed by several minutes. Since Kat is using an after create callback, the job is getting enqueued here, right after inserting the order, but before this transaction commits. Kat happens to be using a job queue adapter that is not backed by the database. And so that means enqueuing the job here is not part of this transaction. And that also means a worker can pick up this job and execute it before the transaction commits. In some cases, that can be pretty bad, and unwanted actions can take place before the transaction commits. In Kat's case, it was sort of fine. The job requires a persisted order. The order is not persisted until the transaction commits, so the job just fails, and it can retry later. But then there's all these statements to update the product inventory, which we've also seen can be kind of slow. And so there's room here for the job to retry and fail multiple times before this transaction commits. That's not great. And Kat has had to configure the retries for this job rather high to accommodate for that, so that eventually, when the transaction does commit, the job will retry one last time and then succeed. But a lot of these transactions are rolling back because of the deadlock errors and lock timeout errors we saw before. And so these retries start to become problematic with these rolled back transactions. Here, the job gets enqueued, but it will never succeed because the order never gets created. So these jobs get stuck retrying over and over until the number of retries runs out. So they're destined to fail, but they're stuck in the queue using up resources. And so what happened here is that the retries for these failing jobs started backing up the queue, getting in the way of successful job runs. And so the work of those successful job runs was getting delayed, like sending confirmation emails. Kat probably needs more job capacity here, but we'd rather our capacity be determined by successful job runs and not all these failed retries. Oh, yeah, there's that. So the simplest thing Kat could have done differently here is swap this after create call with an after create commit, so that enqueuing the job happens after the transaction commits. That looks more like this. Now the job will only get enqueued at all if the transaction does commit, not if it rolls back. And so typically the job will run exactly once. We won't ever need to do this retry thing. Actually, Kat can look forward to Rails 7.2 here, which is going to come with a way to do this by default, to always enqueue jobs after transactions commit. So in that case, Kat wouldn't have had to make any code changes here at all, just upgrade Rails and make sure he's using the right configuration for that. So that's exciting. On Thursday, Kat saw customers complaining about orders getting delivered too late or sometimes with the wrong items in them. And it turns out Kat's team has been doing a bunch of manual work to fulfill the orders, and it's slow and it's error-prone. And so Kat has decided to work with this external fulfillment service. And they have an API that Kat can use to submit the orders. So after saving the order to the Bug Hub database, he adds this call to submit the order to this fulfillment service via a fulfillment client. So this is an HTTP call to an external service inside of a database transaction. And somebody in the front row just made this face. So yeah, that's right. We'll get there. If we look at the queries involved and where this external call gets made, you might notice it looks kind of similar to the job example. And that's because it is. In queuing, the job, in Kat's case, was also an external call. And so this one has some of the same problems. Like, for example, the external call here could succeed, but then this transaction could roll back. So what do you do then? But worse than that, Kat ships this code, and after a while, starts to see errors across all of BugHub. And not just in this new grocery delivery product. It's across the whole site. Kat started digging into this and noticed that this new external fulfillment service that they were using was having some scaling problems. Too many orders were coming in, and the service was just not able to handle them all. Now, it makes sense that this could affect creating the orders, but how is this cascaded into failure across the whole site? Well, as this service got backed up with too many requests, it started responding really slowly, or sometimes not responding at all. Intermittent slowness is somewhat expected for external calls like this. Services can degrade, or they can just be slow all the time, but there's also a network to deal with, and network latency is an issue as well. That's why we often move external calls outside of requests and into background jobs. But when this slowness is happening inside of a transaction, it can threaten the health of your database. That's no good. From the database perspective, the external call is just idle time. Right? It looks like the database is doing nothing, but actually, it's still using up valuable resources during that idle time. For one, it's holding locks. So there's that opportunity for lock contention we talked about before. But the bigger problem in this case is that these open transactions are using up a database connection the entire time they are open, and that database connection cannot be used for anything else. Database connections are a finite resource. So when the fulfillment service degraded, orders kept coming into BugHub, they'd open up a transaction, and they'd get stuck sitting idle, waiting for the fulfillment service to respond. More and more orders came in, the number of connections in use increased, which means that the number of available connections decreased until eventually every single connection was in use. At that point, no other request was able to acquire a database connection. And requests across BugHub, any request that needed access to that database, started failing. Even the connection pooling mechanism in front of Kat's database did not help here, because a transaction is using up one real database connection the entire time it's open. One thing Kat probably should have done here is add a client timeout to this HTTP call. We should never wait an unlimited amount of time for something to respond. And that would have mitigated this to some extent, but there's always going to be some amount of risk having this external call inside of the transaction. So the real solution is to move it outside of the transaction. Now, if this fulfillment service has problems, it's not going to affect the database at all. The transaction only begins if the external call succeeds. So failure of the service will definitely affect creating orders, but it's not going to affect the rest of the site. I also like that it's visually more obvious now that these are two separate operations. It's not one single atomic operation. It sort of looked like it was one unit before, but it really wasn't. It was possible before, as it is now, to successfully submit to the fulfillment client and then have that transaction roll back. Still true. We still have to deal with that, but we can see it more easily now. Like, I don't know, if the transaction rolls back, maybe we need to make another API call to delete the order if the API supports that. That could also fail, though, so maybe we actually want to swap the order of these things and have a different failure mode. In this case, it's possible to create the transaction in BugHub's database, but then have this fulfillment client fail. So maybe we need more code, like have a status on the order that only gets updated after that call gets made, so at least we have some way of finding orders that were created but then not submitted successfully. So there are ways of dealing with this. But yeah, it requires more code to deal with these two separate operations that are not atomic. On Friday, customers start complaining about site reliability. In addition to the problems we've seen so far, they're seeing intermittent 500 responses, slow responses, and they're starting to get frustrated. These problems are stemming from the grocery delivery service's success. It turns out the database is getting overwhelmed by writes on these orders and products tables. So in some ways, it's a good problem to have. Cat meets with the database team, and they decide to split out these tables that are getting so many writes into separate databases. So there's now an orders database, a products database. But that leaves Cat with a bit of a problem here. Because inside of this orders transaction, there's now orders queries and products queries. So Cat does this. Wraps the code in a products transaction as well. And this sort of looks reasonable. Looks innocent enough, looks like it should work, but it's actually a really bad availability risk. Cat can pretty much guarantee he's going to see all the same problems we've seen so far, but they're worse now because any problem is going to affect two databases instead of one. If we have contention problems, slow transactions, external services failing, it's affecting both of those databases. And plus, queries to one database inside of a transaction to another database are yet another type of external call. And so they come with the same problems as other external calls. We've just tied the health of our databases together. And that limits the effectiveness of splitting them in the first place. Furthermore, after shipping this change, Cat noticed that certain products stopped selling because the inventory went down to 0, even though the product was actually still in stock. And that has to do with the fact that these two transactions to different databases are not atomic. They're two separate operations. Now, probably most of the time, they will both commit. Or if the inner products transaction rolls back, that'll cause the outer orders transaction to also roll back. But it's also possible for one of them to commit and the other one roll back. In Cat's case, this products transaction was committing and decrementing the product inventory. But then it turns out that corresponding order never actually got created. That transaction rolled back. And it was actually more common in Cat's application than you might think. That has something to do with the fact that this orders transaction is sitting idle for the duration of the products transaction. And a lot of things can happen during that idle time. Like, you might lose the database connection. Actually, it's one of the most likely places to lose the database connection. You might hit network timeouts, database timeouts, application timeouts, all sorts of things that could go wrong there. So given that these two transactions are not atomic, the first thing I would recommend that Cat do is split them up and do them sequentially. This is not always an easy change to make, but it's a very important change to make. Again, I like that this highlights the fact that these two transactions are two separate transactions, not one single unit of work. The failure modes are the same here, but I can see now what they are. And turns out Cat doesn't like this product inventory getting decremented too far when the order doesn't get created. So, I don't know, maybe he could swap the order of these things. That might be a better failure mode for his application. Of course, now it's possible to create the order successfully and then fail to decrement the product inventory. So we just swapped problems. But maybe that's a better problem for his application. Or again, maybe we need more code now to make these things behave kind of like they are atomic, even though they're not. That's not necessarily easy to solve. So I'm going to skip over it. Good luck. That brings us to the weekend. Cat doesn't work on the weekend. He likes to reflect on what he's learned. What did he learn this week? External calls within a transaction are a risk. Data integrity problems, because these things kind of look like they're atomic, but they're not. Cascading failures, where the external service degrading can cause database failure. These external calls include all sorts of different things. Really, the only thing that should be in a database transaction is queries to that specific database. You don't want much of anything else inside of a transaction. Cat also learned that slow transactions are a risk. If they're inside of a request, they make slow requests. We don't like those. But also, we don't really want slow transactions anywhere, because contention has a way of spreading. A slow transaction in a job might actually slow down a request or create errors in a request. Same thing with this idea of resource exhaustion. Database connections are a finite resource. Database CPU is a finite resource. Transactions that are really slow might be overusing these resources and affecting the rest of your application. I added some slides. I gave this talk before, but I added some slides. Where's Max? Is Max here? Yeah. Kat also likes to look at memes over the weekend. My team thought I should include more memes in this talk, so here's one. My manager gave me this one, Ben Sheldon. Here's another one. Anyway, that brings us back to Monday. Kat had a nice restful weekend, looking at lots of memes. But it turns out over the weekend, a bunch of other teams were making changes to this transaction. Ugh, people working over the weekend. Now it looks like this. Who's seen a transaction that looks something like this? Yeah, okay, a few. You might know that transactions like this are bad for maintainability. Nobody really knows how they work, and nobody wants to touch them. But transactions like this carry a ton of risk, and I think we underestimate how much risk. Could potentially include the risk of bringing down your whole application. So what can Cat do? Oh yeah, don't read this code, by the way. Yeah, I should have said that first, but there's some like clues. Code not meant for reading. Yeah. Yeah, what can Cat do with a transaction like this? Well, one thing I would recommend is that Cat avoid rewriting it from scratch. Instead, try to make small incremental changes. Maybe move one external call outside the transaction, or speed up one query. The idea is to make the minimal change to improve it a little bit, and then repeat. There's some tools coming in Rails 7.2 to help defer work until after transaction commits. I already mentioned this change to in-queue jobs after commit, but there's also going to be a more general purpose callback for deferring work. And this can be a good way to improve your transaction without having to totally rewrite your code. There might be something that's deep inside many method calls that may or may not be inside of a transaction. And so you just defer it until after a transaction commits, and it will work either way now. It's also important for Cat to identify other problematic transactions, because these transactions can affect other places in the application. So most databases have tools for inspecting the behavior of your transactions. MySQL has the performance schema database that you can query, get information about which transactions are slow, which ones are waiting on locks or holding locks, and which ones are sitting idle. So all of that can be useful in figuring out where to focus your efforts. We also added transaction instrumentation to Rails 7.1, and it can be helpful to combine that information with what you get from the database itself. And you can get things like backtraces where the transactions are happening. And then finally, I'd recommend that Cat try to prevent transactions like this from creeping back into his application. There's tools for this, like there's the isolator gem that tries to detect external calls inside of a transaction. You can also build some tooling on top of the transaction instrumentation in Rails. I'll also leave you with some tips for writing safe transactions in the first place. Cat approves of these tips. First of all, keep transactions short. I've talked quite a bit about speed of transactions in this talk. At the end of the day, yeah, if you just take away that transactions should be fast, that's probably fine. Like, just make transactions fast. I wrote ideally less than a second, but that's made up. Like, maybe it depends. More than 5 or 10 seconds, and I'll start to be nervous. Fast transactions means fast queries in those transactions, and not too many of them. Again, made up number, less than 100, might depend. More than 1,000 is probably too many. but I don't know. Really, no external calls at all inside of transactions. It's not a good pattern. Creates a lot of risk, and the failure modes are actually the same if you move those external calls outside of the transaction. Doing the initial move might be a hard change, but ultimately there aren't really any downsides. Really, you want as little code as possible inside of your database transactions. You want to do as much work as you can before or after the transaction. Callbacks can make this a little hard to see sometimes. So when you're writing callbacks, you might want to default to the ones that happen outside of transactions, like after commit style callbacks, for example. And then it's worth it asking yourself whether you really need a database transaction at all for what you're doing. It's often easiest to throw everything in a transaction because it's easiest to reason about. But that doesn't mean it's the best design for your application or for the health of your database. You might need to treat your database as a more sensitive resource and avoid making it work harder than it needs to. So hopefully, these tips will help you write safe transactions, and you can avoid some of the problems that Kat saw and have a stress-free life. Yeah. Thanks. Just going to say, I work at GitHub, not BugHub. Names and species were changed for this talk, but it's all based on real stuff that we have seen and are continuing to see at GitHub. Happy to talk to any of you about any of that. Also want to thank my father-in-law and his friend for doing the illustrations for this. Thanks.